If you've seen any of my videos on smart thermostats, you will undoubtedly know how I feel about off-the-shelf devices. I'm not a fan. This is a fan. One big reason I don't like off-the-shelf devices is that I just don't trust big corporations to be responsible with my data. I also don't trust them to support my product for more than a year before I have to upgrade or the features of my device either get worse or become a subscription-only thing. Basically, the companies that make these devices have absolutely no interest whatsoever in actually delivering any kind of security or reliability to their customers, you and me. So, what can be done? Well, there are two avenues. One, you can simply accept that an old-school thermostat that isn't connected to your Wi-Fi is probably good enough, or you can do what I've done and build your own smart thermostat. The thing is, these devices aren't complicated. They're just a mix of cheap relays, cheap sensors, and cheap radios. The task your thermostat has to perform is simple. When it is too cold, turn on the heat until it's not. When it is too hot, turn on the air conditioning until it's not. And if you want to circulate your air regularly, turn on the fan or blower after a set amount of time and turn it back off after a set amount of time. Now, there's slightly more complexity, but only just. The thermostat has to go a little beyond the target temperature or it will cycle too quickly. Imagine the temperature is set to 70 and it's only 69. The heat comes on and it slowly climbs to 70, then shuts off immediately. When the temperature drops even a little, the heat will kick back on right away. This will cause short, rapid cycling, and that's bad for more or less everything in the system as it uses the limited number of duty cycles all the parts in any machine have. In a traditional bimetallic strip and mercury switch thermostat, there is usually a little magnet or even a small spring that resists the switch being turned off as easily as it's turned on and creates the desired delay so your heat or AC runs a little beyond the target temperature. This isn't really that important to us because in a digital thermostat, you can simply add a little logic to accomplish the same thing. I have already done two of these builds in previous videos, one with a Raspberry Pi Zero W and one with a Raspberry Pi Pico W. However, I found a new relay module that has a case I can modify easily and a larger OLED screen that's easier to read than the last Picostat I made, and it's relatively cheapish. Also, a few people have reached out to me asking me to do another video on the subject and create a simpler code base, so I'm going to do that thing in a minute. First, let's talk turkey, or instead of ugly, tasty, flightless fowl, we could just talk about money. This is an 8-channel relay module by Waveshare that's designed for the Pico. This one cost me $26, but they also sell one that comes with the Pico W already for $35. The OLED screen I'm using was $22, but that's because I bought it from a different source than the Waveshare Store. I'm not sure they still have this particular size, but they have many similar sizes and most of them use the same driver chip, the SSD 1305 or SSD 1306, if you don't want to pay quite so much for the screen. The sensor I'm using is a regular old run-of-the-mill DHT22 temperature and humidity sensor. I will link to all of these parts in the description. Affiliate links, of course, so I do get a small amount from Amazon, but I'd get that regardless of brand, and you won't pay any more using those links. I didn't link to the header pins or buttons I'll be using because of availability and prices for those things. They tend to fluctuate quite a bit, and they're not really hard to find online. Okay, with that out of the way, let's build a smart thermostat through the amazing power of the montage. First, we have to solder on the header pins. I use another breakout board I have for the Pico to hold everything nice and straight while I solder. Notice that the header pins I'm using are long on both ends. This is necessary to connect other things to the Pico while it's seated in the relay module. Now, I can go ahead and unscrew the cover for the module and install the Pico. Next, I'm going to start adding the necessary wires for the OLED screen. Pin numbers will be in the description. I'm connecting the screen just for testing, which I forgot to take video of, but it works. The next thing I need to do is make a cutout for the screen to sit in. I took the Mark Watney approach here, minus the jumping on it. There are better ways of doing this, but I was too lazy to get my rotary tool and bits out, so I just did this thing. You have to admit, it is fun to watch. After I clean up the edges with a whittling knife, the screen will fit quite nicely. Now I connect the wires to the screen again and put it all together as a test fit. Being satisfied with the fit, I hot glued the screen and wires in place on the cover. Next, I have to connect the DHT22 sensor. Again, pinout will be in the description. Now, it's time for another test fit. Next, I'll need to drill holes for the buttons. I could have drilled these holes a little straighter, but I didn't really care enough to. Then, I'll install the buttons. I'll need to solder jumper wires to the switches so I can connect them to the Pico. Here, I'm bending the posts on the switches so I have more clearance when I put the cover on. Sorry for being slightly out of frame. I'll solder a short wire to all of the switches for the shared ground. Now the jumper for the ground. Then I'll solder the jumpers for the GPIO pins. Next, I'll go ahead and connect the buttons to the Pico. Again, pin numbers in the description. Of course, now it's time to shove everything into the case without shorting anything. It's also a good idea to make sure you have the case in the correct orientation. It can be very tricky to get everything inside to fit without mashing pins or jumpers, but it will all fit. Mark my words. Here, I'm screwing in 2 of the cover screws so I can test before securing it completely, which I forgot to take video of, but I did put the other 2 in. Now it's ready to power up. I have already put the code necessary on the Pico earlier. That code is available on the GitHub linked in the description. And now I have a working smart thermostat capable of working independently or in conjunction with other systems. There is Home Assistant functionality in the code for setting the temperature high and low, but you could use this without or modify that code to work with a different API. I excluded MQTT from this build because I don't use it anymore. Everything in my current system simply uses HTTP or TCP over socket communication. One thing I want to note about the wiring. When I was connecting the screen jumpers in the video, the ground and 3.3 volt wires were not present, and I didn't take any footage of adding them because I just did it while testing without thinking about it. I did include them in the list in the description. You could also take the Waveshare sticker off of the cover, but make sure you have some Goo Gone at hand to get rid of the super sticky adhesive underneath. So there you have it. It's another very simple build that should cost only about $50 or $60, and it gives you absolute control over your smart thermostat and how it works. You don't have to worry about Google getting bored of supporting your device, and you can just adjust the logic however you see fit. Also, there are 8 relays and the thermostat only requires 2 or 3, depending on if you have a fan wire. So you could potentially control multiple units or other devices like radiant heat flooring, a humidifier, a dehumidifier, some other air mover, or nearby lights. You could do all kinds of things with this device. This relay module I've set up with code that pulls the state of Home Assistant toggle helpers and simply turns the corresponding relay on or off. I'll link to the code for that in the description as well. You don't need the DHT22 or OLED for that to work, just a Pico and a relay module. Before I close the video, I want to show you how I installed the new Picostat in the game room to control the small HVAC unit there. After mounting the device to the wall, I run the hot wire, usually red, to all of the center terminals of the relay for heat, fan, and air conditioning. Then I run the heat wire, usually white, to the normally open terminal on the first relay. Run the fan or blower wire, usually green, to the normally open terminal of the second relay. Last, run the cooling wire, usually yellow, to the normally open terminal of the third relay. For me, that's all, but some of you may have another very useful wire. In order to power my thermostat, I have to have an external power supply plugged in nearby or come up with some other solution. But there's another way. If you have the black common wire, you can use an AC-DC converter or rectifier to convert the 24-volt AC to DC and a buck converter to step that down to 5 volts DC to power the device. There are convenient terminals on the relay board for just such an occasion. Bonus round. If you don't have the black wire, but you want to be able to do this, and you have the skills and access, you can actually run your own common. All furnace control boards have the terminal for it, but most times the wire just isn't necessary, so the installers don't run it. I might do this in a later video, but for now, because my outlet is right beneath the thermostat, I'm going to leave it ugly. After all, it's still prettier than the last throw together I used for a year and a half. I really hope you enjoyed the video, and I especially hope you've learned something or been inspired to do a thing. If you have enjoyed it or been inspired, maybe consider shifting the pixels that make up your mouse cursor to an icon representing a gesture that means way to go, and give it a good click. If you really find me entertaining, maybe subscribe so YouTube knows I'm neato. I do hope you'll join me for future videos as I continue building and exploring smarter circuits.